morning, good afternoon, or good evening, ladies and gentlemen. I hope you're doing well. Welcome back to Unit 7. Now, we have already covered lessons 7.1, 7.2, and 7.3, so please take a moment to go back and review those if you need to. Today we're going to be discussing lesson 7.4, which is all about graphing motion. So let's get started on that. All right, so the first thing, let's review just what is a graph. Well, a graph is a visual representation of the relationship between two variables. I know you probably know how to draw a graph already, but it's a good idea to go back and review the basics before we start applying some meaning to it. Now, you're probably used to labeling graphs with the x-axis being the horizontal axis and the y-axis being the vertical axis. In physical science, we will usually call the horizontal axis time, and then the vertical axis can be anything that changes over time. So, for example, position or velocity. If you're accelerating, then your velocity is changing over time, and if you're just moving, then your position is changing over time. Take a moment to review how to plot a point on a graph. Remember that points would usually have two coordinates, an x-coordinate and a y-coordinate. The x-coordinate is typically given first, followed by the y-coordinate. So let's say that you had this graph and you wanted to plot the point 4, 7. 4 being the x-coordinate and 7 being the y-coordinate. Well, this is the x-axis down here, so to find the x-coordinate, we're going to move along the x-axis until we get to the number 4. To find the y-coordinate, we're going to move up the y-axis until we get to the number 7. And where those two lines meet is the location of our point 4, 7. Now, sometimes we'll be given information on a table and we have to plot that information onto a graph. So, for example, on this table, we see that an object is moving, its distance is changing. We're given several different times and the distance that the object has traveled after each amount of time. So we will plot those points on the graph and see if we can get any additional information about the object's movement. We'll start with 1 second and 8 meters. Then 4 seconds and 17 meters. 6 seconds and 23 meters. And finally 10 seconds and 35 meters. Okay, so looking at these 4 points, it appears that they lie along a straight line. Now, we can't be 100% sure. It's possible, of course, that the actual shape of the object's motion is a squiggly line that just happens to pass through these points that lie in a straight line. But the more points we get that all lie along a straight line, the more confident we can be that this object's motion is described by a straight line. And we'll talk about what that means in just a minute. So if we were to assume that this object's motion is described by a straight line, we can go ahead and draw that line. There it is. And we can use this line to make predictions about the object's distance at any time that wasn't explicitly given to us. So for example, if we wanted to guess where the object would be after 5 seconds, we can draw a line straight up from 5 seconds, and where it intersects the graph, make a hard left turn and go over to the vertical axis, and we find out that after 5 seconds, the object should have traveled a distance of 20 meters. That information was not directly given to us. We found it by using a graph that was drawn with the information that was provided. We call that interpolation. Whenever you use data to infer the existence of a data point that is within that data, that's called interpolation. If I tried to predict a data point that was outside the initial set of data, that would be called extrapolation. But you don't have to worry about that. It's not on the test. Alright, so the next thing we want to talk about is how to find the slope of a graph. Finding the slope of a graph usually involves a couple of steps. The first thing you want to do is you want to pick 2 points that are on the graph. It doesn't really matter if you have a linear graph like this, it really doesn't matter which 2 points you pick. You're always going to get the same slope. So just arbitrarily, I choose this point and this point, and I label this point 1 and this point 2. Generally speaking, the point that is further to the left, you want that to be point 1. And the point that is further to the right, you want that to be point 2. But it doesn't really matter. It's just a convention to do it that way. Now the next step is going to be to calculate the rise. And when I say the rise, I mean how much does this line climb up vertically between these 2 points? In other words, what's the vertical difference between point 1 and point 2? So to find the rise, I would take the y-coordinate of point 2, which looks like it's going to be 23, and I would subtract the y-coordinate of point 1, which looks like it's going to be 8. Right, so the rise will be 23 meters minus 8 meters because the y-axis is measured in meters, and the difference between those is 15 meters. The line climbed 15 meters between point 1 and point 2. Now if the line had been sloping downward, then the y value for point 2 would be less than the y value for point 1, and in that case the rise would wind up being a negative number, and that's perfectly fine. The next thing you want to do is to calculate the run. The run is the horizontal difference between point 1 and point 2. So we would take the x value for point 2, which is going to be 6 seconds, and we would take the x value for point 1, which is 1 second. We'll subtract those to get a run of 5 seconds. If point 1 is to the left of point 2, then the run is going to be a positive number. If we had chosen this is point 1 and this is point 2, then the run would be a negative number, and that's okay too. It'll all come out in the wash. To find the slope, we divide the rise by the run. So our rise was 15 meters and our run was 5 seconds. The slope is 15 meters divided by 5 seconds. 15 divided by 5 is 3, and meters divided by seconds is meters per second. So the slope of this line is 3 meters per second. Well, hey, meters per second is a unit for speed or velocity. So by calculating the slope of this line, we have calculated the velocity of the object whose motion is depicted in this line. The graph we just looked at was called a distance versus time graph. And that's exactly what it is. It's a graph that displays the motion of an object, the distance traveled by an object over time. You can abbreviate a distance versus time graph as a DT graph. Sometimes you will see it called a position versus time graph or a PT graph. Position versus time graphs are slightly different, but they can show the same information: whether an object's moving, how fast it's moving, where it started, where it ended, all that good stuff. As we just learned, the slope of a straight line distance versus time graph gives you the velocity. And if the line is sloping upwards, then the velocity is positive. And if the line is sloping downwards, then the velocity is negative. In other words, the object is moving backwards. If a distance versus time graph is curved, then that tells you that the object is accelerating. And we'll take a look at some examples of that in just a few moments. So we're going to look at the motion of two objects represented by this green ball and this purple ball. And as they travel, we're going to keep track of the amount of time, and we're going to draw distance versus time graphs for both objects. So here we go. Now you can see that the green ball is clearly traveling faster. It covers more distance in the same amount of time. So when we compare the distance versus time graph for the green ball to the distance versus time graph for the purple ball, we see that the DT graph for the green ball has a steeper slope. Both objects were traveling at a steady velocity, a constant rate of speed, so they're both represented by straight lines. There was no acceleration, but the green ball was accelerating more rapidly. Excuse me, I said that wrong. The green ball was not accelerating, but it had a higher velocity, so it has a steeper distance versus time graph. Let's take a moment to familiarize ourselves with 5 common distance versus time graphs, just so we can kind of get an idea what each one represents. So first, if we see a distance versus time graph represented by a straight line that is sloping upwards, that indicates constant positive velocity. As time passes, the object's distance is increasing by a steady amount each time. If we see a distance versus time graph that is a flat line, that indicates zero velocity. In other words, the object isn't moving at all. Whatever distance it is at from the starting line, it's just staying at that distance. If we see a straight line that slopes downward, then that indicates constant negative velocity. The object is still traveling the same distance for each amount of time, but it is heading back towards the starting point instead of away from it, so the line slopes downward. If we calculate the slope of this line, we would get a negative number. Now, if we see a distance versus time graph that is curved, that indicates acceleration. It could either be speeding up or slowing down. If the line curves upwards, that indicates positive acceleration. If you pick any 2 points and calculate the average velocity between those 2 points, as you go from left to right, you see that the slope between those 2 points gets steeper and steeper and steeper, indicating that this object's velocity is becoming more and more positive as time passes. So we have positive acceleration. On the other hand, this graph shows negative acceleration. As time passes, the slope between any 2 points becomes flatter and flatter, and finally at the end, the slope is almost perfectly flat, indicating the object has come to a stop. So next, let's talk about velocity versus time graphs. A velocity versus time graph, also known as a VT graph, compares velocity to time. So it doesn't show you how far an object has traveled, but it shows you how fast the object is traveling over time. The slope of a VT graph, or velocity versus time graph, tells you the acceleration of the object. And for each distance versus time graph that we've looked at, there is a matching or corresponding velocity versus time graph. So let's take a moment to compare the distance versus time graphs and the velocity versus time graphs for several objects, and we'll see if we can match them and see the similarities. Let's start with positive velocity, constant positive velocity. So as we said a minute ago, constant positive velocity is represented by a straight line with a positive slope. The velocity versus time graph shows that the object's velocity is steady over a period of time, and that's exactly what we would expect. A straight line represents constant velocity. This graph is just showing us what that velocity is as time passes, and it's a steady 2.5 units of velocity, whatever it is, meters per second or feet per hour, or whatever you want it to be. Now let's look at negative velocity. We have a straight line with a negative slope, indicating the object does have a steady speed, but it's traveling in a negative direction instead of a positive direction. So this time, the velocity versus time graph is still a flat line indicating a constant velocity, but it is below the horizontal axis instead of above it. It is a negative velocity that is not changing over time. Zero velocity, the object isn't moving at all, which means that its distance versus time graph is just a straight, flat line. It is staying at a constant distance, in this case of 25 units for the entire 10 time units, seconds we'll assume. If we look at a velocity versus time graph for the same amount of time, its velocity is steady at 0. The object is not moving, it's not accelerating, it's not speeding up or slowing down, so its velocity is a steady 0. Now let's compare positive acceleration on a distance versus time graph and a velocity versus time graph. On the distance versus time graph, we see that the line is curving gently upward, indicating that for each little tick mark on the time, the object's velocity is getting faster, faster, faster. And this is what we see on the velocity versus time graph as well. As time passes, the object's velocity is getting steadily faster. Now notice that acceleration on a distance versus time graph shows up as a curved line, but on a velocity versus time graph, uniform acceleration shows up as a straight line, because the velocity is changing by the same amount for each unit of time. But the distance is changing by increasingly larger amounts for each unit of time because the object is speeding up. And finally, let's look at negative acceleration. So we have an object that starts off with a pretty high rate of speed, but then as time passes, it slows down and the distance traveled between each unit of time gets smaller and smaller and smaller until finally the object reaches a standstill where it's not moving at all. And that's what we see on the velocity versus time graph. We see that as time passes, the object's velocity gets slower and slower and slower until finally at the end it reaches a velocity of 0. Remember, the slope of a velocity versus time graph gives you the acceleration. And we can see that the slope of this line would be negative, which is exactly what we would expect given that this object is slowing down over time. And that's going to be it, folks. That is the end of lesson 7.4. I would encourage you to go back and review the other lessons in this unit, lesson 7.1, 7.2, and 7.3. Tomorrow we will move into Unit 8, which is going to be all about forces. So we will be defining forces. We'll talk about Newton's laws of motion, how forces cause motion to change. If you have any questions, please don't hesitate to reach out and contact me. As always, there will be a brief assignment in Google Classroom. Please take a few minutes of your time to complete that assignment. I will come back to you and offer feedback as quickly as I can. I hope you're all having a great day. Good to talk to you. Remember to stay safe. Keep washing your hands. Talk to you tomorrow. Take care. Bye.